Good afternoon. This is Ward Harriman, AE6TY. Thanks for tuning in. Over the last several months, I've been adding support for surfaces to SimNEC. Now, before embarking down this path, I asked a simple question: why? Most every NEC front end uses wire meshes to model complex surfaces, and these models have been assumed to be predictive. But there are problems with wire meshes. The first problem is that in order for meshes to be reliable, the wires must have the correct diameter, which is based on their spacing. With complex surfaces, the wire spacing varies greatly. Second, NEC 2 and NEC 4.2 do not deal well with wires which meet at acute angles. Complex surfaces almost always result in these angles. And third, to even begin to understand when to use surfaces, you pretty much have to be able to use those surfaces. Thus, in order to find out if they are useful, I had to support them. As a teaser, here are some uses for surfaces using NEC 5. Now, I'll warn you that surfaces can require large amounts of processing power, so I will be editing out any exceptionally long load times. The first example is a loop antenna. Here's a typical loop antenna. It's very thick. It's not your made out of 3/4 inch copper pipe, but this shows you how NEC surfaces can be used to model it. And I can change the resolution of the triangles simply by playing with these parameters. Another example, more in the microwave domain, is a model developed by Dan McGuire. Again, I can play with the resolution of these triangles. Another example. And finally, one which I know will take a long time to come in. I can use this capability to model the area around my antenna. This will take a while to load, and I will edit it out. Here it is at low resolution. I'll turn off the field. And I'm going to turn on high resolution. I'm going to come down here and edit this to put in a high resolution picture. Many more triangles. And this will take some time, and I will definitely edit this out. Okay, it's back. As you can see, it has substantially more resolution. It's not clear it has more information, but this is one of the things you can play with. Okay, one final example. Is a NEC 5 version of a horn-fed parabolic. You see the gain is about 25 dB. And just to give you a picture of what it looks like in NEC 2 or NEC 4.2, I can change these patches down here into wires. This takes a while. And let's turn off currents and no dots. You can see what the wire mesh looks like. Here's a wire mesh that was generated automatically. You can see that it tries to keep the triangle sizes basically the same for the entire surface. Doesn't do too bad a job. Surfaces are best developed interactively. So in this video, I will have a NEC display, a development window, and I'll be writing things over here and you'll be able to see how it's coming up over here. Let's get started. All right, here we go. I have a basic dipole. I'm not going to look at the field. I'm not going to look at the elevation. Let's just find it. Here's my dipole in free space. So there are three types of surfaces in SimNEC. There are patches, there are cones, and there are spheres. A patch is the simplest surface to understand, and it is either a 3 or 4-sided polygon. So I can write a patch. We're going to do a patch equals. Okay, so a patch takes at least 3 points and at least one segmentation number. So I'm going to put in a patch that starts at 0, 0, 0. I'm going to want 5 segments along this end, and I'm going to go to, say, 10, 0, 0, and then I'm going to go to 10, 10, 0. This will be a triangular patch. You can see it crops up over here. Let's look at it in the Z direction. This is pretty much what we expected. I can come over here and change this a bit. Let's say this is -5. And so you can see the patch is pretty much what I've described. And I'm going to add another point to make this a quadrilateral, and that would be at 0, 10, 0. And there's my basic patch. This can be modified in lots of different ways. For example, it doesn't have to be square. So if I were to say this last point was at 15, was up here, 15. I can also say how many points I want along this edge. Right now it's assuming 5 because that's the only number I've given it. But if I give it another number, I can say 7. And now I have 5 along this edge and 7 along this edge. And I can do one more thing, which is I can specify the number of segments along this side. Let's make it even bigger. And so now I have 5, 7, and 10. And if I zoom in here, you'll see that it has to make up some more lines kind of along the way. And again, it's trying to keep the triangles basically the same size. These don't have to be collinear. So for example, I can say this point is 3 in the Z direction, which of course you can't notice here. But if I do a look down the X, you can see that this is kind of a warped surface. They don't have to be coplanar. They don't have to have the same number of segments along each edge. It's a pretty general purpose kind of thing. Now the next simplest surface to explain is a cone or a cylinder. I'm going to write the simplest cone here that I can, which would be a cylinder. So I'm going to say it's a cone. Now I have to have an axis for the cone. I'm going to make the axis 0, 0, 0. How many points along this axis? Let's say 5. And the end axis is 1. So it's going to go from 0 to 1 up the z-axis. And now it needs a radius. Well, we don't give it a radius in SimNEC. You give it a point on the side, and I'm going to say the point on the side is at 1, 0, 0. And here we have our cylinder. It's got 5 sides. It's got 5 increments along here because I only gave it the number 5. Let's make it a little taller so it's easier to see. And we can change the number of things around it by specifying another number in here. Let's say 8. Sorry. let's say 8. So now I have an 8-sided figure. And I can change whether it's a full circle or not by simply putting in the number of degrees. I'm going to make the number of degrees 90. And you can see that now I have a cylindrical object going from 0 to 5 with some number around the bottom, some longer around the side. Now there's one more thing that I can do. If I make this a circle again, I can actually make this a cone. So we said that the starting location was here. And if I say the ending location is out here, I should get a cone. Ending location is 3, 0, and it's got to be at the same level, so let's say height is 5. And you can see now that I've made a cone. I can make a cone have 0 down here if I wish. Okay, so let's change this back to being 1. Actually, let's get rid of this altogether. Now there are times when you need to join cylinders together. For example, we saw in the loop where we had a bunch of cylinders which were connected, and I can bevel this side by simply changing this start point down here. So if I start this at 1, you'll see here's the starting point for it, and it beveled it, and it matches the bevel at the other end. But I don't have to have it match the bevel at the other end. I can make it be I'm sorry, I'm going to make it be 2, 0, 5. And you can see it's square. If I make this 4, now we'll end here. So I can shape this tube in many different ways. I can change the radius along the way, I can change the bevel along the way, and I can control the segmentation. So the third shape SimNEC provides is the sphere. And when describing a sphere, we use the terminology of the globe. So we're going to say it's a sphere. Let's start it at location 0. Let's say that I'm going to specify the North Pole. I'm going to say it's at 0, 0, 5. It needs one more argument, which is the segmentation. Let's say 9 for the time being. And here's our sphere. The sphere can be truncated in a variety of different ways. It can have only a certain number of latitudes and only a certain number of longitudes, and I can specify that, but in order to specify that I have to first specify the number of longitudes. It's just the way it works. Let's make this 36. There's our sphere with 36 around, 9 high, and now if I want to limit the range of it, I can specify the latitude north and south. So let's say it's 45 degrees north and it's 23 degrees south. Here's my truncated sphere. As with latitude, I can specify the longitude. Let's start at the prime meridian and go 90 degrees to the west. And if I look at this from here, here is the prime meridian. Looking at it from the North Pole, we get down to 90 degrees west. Now the sphere can be placed in lots of different orientations. Let's do the first one. Let's go back to the basic sphere. Here's my basic sphere. And suppose I want the North Pole, in fact, to be along the x-axis. Well, I can simply make that true. I can say we're going to put it along the x-axis. Let's make it bigger. 5. So here I've aligned it so that the center is at 0 and the North Pole is at 5, 0, 0. Now, specifying the North Pole is kind of a little strange, but the reason for this is so that it's simple to get the North Pole to be where you want the North Pole to be. So up here, look at my dipole. I have a left side that's at dollars left and a right side that it's dollars right, and I've set those right here. And suppose I want to make this sphere hang off the right-hand side. So what I'm going to do is I'm going to say I want the right-hand side to be at dollars. I'm going to add some, but I'm going to move the center to be over here somewhere. I'm going to place the North Pole at the right-hand side, and I'm going to say it's 9. And lo and behold, I've set my sphere right here. Likewise, let's put a sphere at the other end. I'm going to move the center to be to the left, and I'm going to put the North Pole at the left. And there we have it. Now, one of the interesting things about being able to do this all interactively is that you start to notice some strange things. So, for example, if I look straight down this axis, you can see that this sphere's currents and this sphere's currents are not the same. Notice this one has more current flowing on it over here. And if I move this feed point, I can change the current distributions. Let's put the feed point at the middle. Pretty much the same. Definitely different. So you get to see things that you would not otherwise see, which of course may be a distraction, but nonetheless. So finally, SimNEC provides the ability to move and scale these surfaces, and this was how the opening video was created. Over the last several months, I have added NEC 5 surface support to SimNEC. This new capability eliminates many of the problems previously associated with using wire grids to model complex surfaces. Hopefully, this will expand the range of problems SimNEC can address and lead to more understanding by the user base. This is Ward Harriman, AE6TY. Thanks for watching, and thanks for using SimNEC.